Welcome back to the course on Fundamentals of Artificial Intelligence. We continue our discussion on search strategies. Having introduced uninformed search and heuristic functions, in this lecture we would cover informed search strategies. Informed search strategies use task-dependent information and are also called heuristic search. We would first look at heuristic search. We would thereafter look at the types of heuristic search. We would typically do two interesting types. First, the best first search. We will discuss algorithm A and thereon define algorithm A star. We would then look at local search and discuss hill climbing and simulated annealing. Uninformed search methods that we have discussed so far, whether breadth first or depth first, are exhaustive methods for finding paths to a goal node. These methods provide a solution, but often are infeasible to use because search expands too many nodes before a path is found. On the other hand, we have informed search methods which use task-dependent information to reduce the search. The task-dependent information is called heuristic information, and search procedures that use it are called heuristic search methods. We are interested not only in minimizing the cost of the path, but also the cost of the search required to obtain the path. That is, we are interested in minimizing some combination of the two. Search methods that minimize this combination average over all populations is what we are likely to look at today. Heuristic information is used so that search expands along those sectors of the frontier which are thought to be most promising. As I told you before, we call them heuristic search for they use task-dependent information. In a heuristic search, each state is assigned a heuristic value, a value that somehow reflects its importance in the search and is used in the search to select the best next step. A heuristic is an operationally effective nugget of information and directs the search in a problem space. We have looked at heuristic functions in great detail in our last lecture. We continue here with a review. The heuristic function, written as h of n, estimates the cost to a goal. The most promising states are selected. For ordering nodes for expansion in our search, we need a method to compute the promise, and this is done using a real valued evaluation function. Evaluation functions have been based on a variety of ideas. Like for the 8 puzzle, we had discussed and defined an evaluation function such as counting the number of misplaced tiles. The best first search that we will discuss first in our informed search strategies is a way of combining the advantage of both the depth first and the breadth first search into a single method. We need to recall that depth first is good as it allows a solution to be found without all competing branches having to be expanded. On the other hand, breadth first is good because it does not get trapped on dead end paths. We want to combine this in a best first search and follow a single path at a time, but switch paths whenever some competing path looks more promising than the current one. That's the philosophy of breadth first. Take the best of the depth and the best of the breadth first searches and jump from one branch of the search to the other branch to get to the best nodes at every point in time. The idea is to use an evaluation function for each node that estimates the desirability and then expand the most desirable unexpanded node. We order the nodes in decreasing order of desirability, and one of the special case is the A star search. Let's look at an example here. Let's say we have a problem and where we are searching a tree and a node is expanded to give us node B, node C and node D. Let us now try to compute some heuristic function that gives us a value of these nodes, the heuristic value of these nodes. So let's say B has a value of 3, C has a value of 5 and D has a value of 1. The next thing that we would love to do, if these values reflect somehow the distance to the goal, we would love to expand node D, for it has the minimum of the distance to the goal. So we expand D, and let's say we end up having two nodes E and F, and let's say these heuristic values that I get of the evaluation function at node E and node F is 4 and 6 respectively. Now if you compare the heuristic values at B, which is still unexpanded, at C, which is still unexpanded, and the unexpanded nodes E and F, we see that B looks most promising, and therefore a best first search would expand B rather than expanding E or F as it would have been done in case of a depth first search. Therefore, the next thing that's expanded is B, and let's say we have a node out of B which is G and H, and if we look at their heuristic values, then we have 6 and 5. In that case, interestingly, once again the search would jump back to E, because if you see, G has a value of 6 whereas H has a value of 5, and E looks most promising at this point of time. The search would then expand E. This is the basic idea of a breadth first search. To once again reiterate what I have just now said, in a breadth first search we do go about looking at expanding every node as I did for the first time, but then out of this I decided to go and take down D, not B or C, as D looked most promising, and I expanded its nodes. But while doing so, I jumped back to the node which was not expanded and even looked promising. So from doing D and not doing E and F, I jumped back from here to expanding B. And once B was expanded, I realized that nodes G and H are less promising than E. I come back and expand E. So this is what a breadth first search does. It tries to expand the best promising node while shifting from being depth first to breadth first and breadth first to depth first again. So if you recall, we had introduced this graph search algorithm where we had said that we will have two lists, one called open and the other called closed, on which we shall maintain the nodes that are to be expanded and that have already been expanded. So here, continuing that discussion, as I am dealing with A, B, C, D and then expanding E and then going back and expanding B, the only point in which this algorithm of graph search would make a difference is on the reorder of the open list. When I reorder the open list, I will now order it according to the heuristic merit, and therefore, the node that would be expanded next would be at the front, allowing me to take the most promising node first. Algorithm A is about avoiding expanding paths that are already expansive, and here the evaluation function can be defined so that its value at any node estimates the cost of the minimal cost path from the start node S to the node N. So, that is the minimal cost path, and together with it the cost of the minimal cost path from the node to the goal. So, algorithm A is about, like, if you have a start node here and somewhere down the line, down there you have a goal, then the evaluation function that I use for algorithm A is about an estimate of the cost that I need to expand to come to this node, and it is about the cost of coming from here to that particular node, and then the cost of going from this node to the goal. And this estimate gives me the value of the evaluation function. Now, if you look at this very closely, you would realize that what I am trying to emphasize here is the point that the evaluation function Fn is an estimate of the minimal cost path that goes through node N at this point of time. So, in order to get this more correctly, let us introduce some notations. Let us say we have a function k n sub I and n sub j that gives the actual cost of a minimal cost path between two nodes n sub I and n sub j. Now, the cost of minimal cost path from node n to some particular node t sub I is then given as k of n t sub I. H star n is the minimum of all such paths over the entire set of goal nodes t sub I that I could generate, and that is the heuristic value. So, H star n is the cost of the minimal cost path from n to a goal node. That is the cost of an optimal path from a given start node S to some arbitrary node n. So, that could be written as k s n, and we write this as g star n. So, g star n is the cost of the optimal path from a start node to a node n, and together with h star n we define f star n, which is the actual cost of an optimal path from node S to node n plus the cost of an optimal path from node n to the goal node. So, it has two things that I had just now told you in the previous slide. I have the start node S, and somewhere I have an intermediary node n, and down the line I have a goal node G. So, I take this as g star n, the cost of coming from the start to n, the optimal cost, and I take this, the cost of going from n to the cost of going from n to g, which is h star n. The evaluation function f star is defined as g star n h star n. Now, the evaluation function f is an estimate of f star, and this estimate can be written as f is equal to g of n plus h of n, where g of n is the cost so far to reach n and actually is an estimate of g star. H of n is the estimated cost from n to goal and is an estimate of h star. And for h, this estimate alone, we rely on heuristic information. Given these two estimates, we have f of n, which is the estimated total cost of a path through n to the goal. Any graph search algorithm using this evaluation function for ordering nodes is called algorithm A. If now you take the lower bound of h star, that means when you estimate h, you take the lower bound of the estimate for all nodes, then algorithm A will find an optimal path to the goal. When algorithm A uses such an heuristic function, that's a lower bound on h star, we call it algorithm A star. The best first algorithm that I had little while ago described is a simplification of algorithm A star. Now it's interesting to note that if we take h equal to 0, which is certainly a lower bound on h star, we end up having breadth first search, finding minimal length paths. The breadth first search, therefore finding minimal length paths, follow as a special case of this. So let us try to understand the A star algorithm. The evaluation function f of n is written as g of n plus h of n, where g of n is the cost from the starting node to reach n, whereas h of n is the estimate of the cost of the cheapest path from n to the goal. So here h of n is an estimate, it's a heuristic value. So if you see, we can be very sure of gn, whereas hn is an estimate. Let's try to understand this by solving our favorite 8 puzzle using the A star algorithm. Here is a start state and here is the end state that I want to reach. Now just to remind you of the 8 puzzle game that we want to solve here, we want a path from the start to the goal. Now when we want a path, we are able to operate on this blank space. Given a blank space, we could lead this state to newer states. So let's see how many states we can end up with. So on moving 1 down, we have 1 state. On moving 4 out, we have another state. Moving 7 up, we have a 3rd state. Now the question is, given these 3 states, which is the state that I expand next? Recall that the A star algorithm uses an evaluation function which is written as f is equal to g plus h at every node n. So we start computing g, the cost of reaching the nth node, and h, the estimate of going from n to the goal node. Let's do it for each of the nodes that we have expanded. So at the first node, to start with, g is obviously 0. We have not expanded anything to come to this node as of yet. And let's take h, the heuristic, which we will try to count the misplaced tiles, the number of misplaced tiles. So we want to count the number of misplaced tiles as our heuristic function, h. So in here, if you compare it with the goal state, we could see that 1, 2, 3 are in its place, 4 is not in its place, then 6 is in its place, 7 is in its place, 5 is not in its place, and 8 is not in its place. So the number of misplaced tiles here counts as 3. Given the fact that I have not expanded anything to come to the node and my heuristic value which I have stated as number of misplaced tiles, as some heuristic or estimate of going from n to the goal node, I have counted as 3, the evaluation function will have a value of f equal to g plus h, which is 3. I compute the other heuristic values here. So, at this point g is equal to 1 and h is equal to 4, and I end up having f equal to 5. At this point I have g equal to 1, h equal to 2, f equal to 3, and at this point h is equal to 4 and f is equal to therefore 5. Just for a cross check, I just want to show you one more time counting of the misplaced tile heuristics. Here if you look at the number of misplaced tiles, 1, 2, 3 are in its place, 4 is in its place, 6 is in its place, 7 is in its place. Only tiles which are not in its place is 5 and 8. Therefore, I have an h of 2 and leading to an f of 3. Depending on the value of f, I pick up this middle state there, and we expand this node to get 3 newer nodes and then compute the heuristic values of each of them. Note that at this point g becomes 2 and I count the number of misplaced tiles to know about h. That leads to f equal to 3, f equal to 5 and f equal to 5 again for the last node here. Therefore, I decide to expand this node at the start. When I do this, I end up having 2 nodes, either moving 7 to the blank or moving 8 to the blank, and one of them is the goal node. That you can still see by computing the heuristic function, and you would have g equal to 3 at this point of time. You would have 2 misplaced tiles here and therefore f is 5. In this node we have g equal to 3, h equal to 0 and f therefore is 3, and this is what I would ideally take for expansion, but then I will realize that that is the goal node and my algorithm will end. So, what we have realized is that this A star algorithm could take me to goal in such a nice directed way. The g that I am using in the A star algorithm lets us choose which node to expand next on the basis not only of how good the node itself looks as measured by the heuristic function, but also on the basis of how good the path to the node was. Therefore, g carries a lot of weight. The estimator of h star, the distance of a node to the goal, is another interesting observation. If h is a perfect estimator of h star, A star will converge immediately to the goal without no search. Better the estimate of h, closer we would be to the direct approach. On the other hand, if h is 0, the search would be controlled by z, and if g is 0, we would end up having random search. If we consider g at every step to be 1, we would end up having a breadth first search.